MATU 206, Week 6, Chapter 5. Integers and the operations of addition and subtraction. An integer is denoted by the letter I, and an integer is the natural numbers 1, 2, 3, 4, and the whole number 0, and the opposite of the natural numbers, or the opposite of the positive integers. Numbers are broken up into different things. The smallest group is natural numbers, and those are 1, 2, 3, 4, 5, 6, as babies would naturally learn to count. The next concept we add on are the whole numbers, and that includes 0 and all the naturals. Then next thing we do is the opposites of the naturals, or the integers. And so integers are all the natural numbers, 1, 2, 3, 4, the whole number, 0, and the opposites of the natural numbers. And then we have this set here, and this is anything we can make into a ratio. So it's fractions, terminating decimals, repeating decimals, and then the overarching branch there is these are the rational numbers, meaning they can be made into a ratio, the root word there, ratio. And we have the irrational numbers, which are non-terminating, non-repeating decimals. Some examples are pi, which is 3.14 ... goes on forever, never stops. Any square root of a non-perfect square, so square root of 17 is irrational, because if you calculate that out, it will keep going. It will not terminate, and it will not repeat. So that's irrational. And these are all real numbers, as opposed to imaginary numbers like I, which is used to find the square root of -1 equals I. So the set of integers is denoted by I. It is all the whole numbers, or natural numbers, 0, and the opposites of the natural numbers. Some people represent integers using a chip model, where black chips represent positive and red chips represent negative integers. Each pair of black and red chips neutralize each other. So we would say that red and that black, in my terminology, I call it a 0 pair. I don't know what this book refers to them, other than that they neutralize each other. So a 0 pair, basically they neutralize, they cancel each other out. So we have 3 0 pairs. We're left with just one red one, which is a negative. So -4, those 4 red ones, plus 3, those 3 black ones, they'll leave -1. There's also the number line model of this. Positive integers are represented by moving to the right on the number line, and negative are represented by moving to the left. So -3 minus 5, if you have -3 and you're taking away 5, you start at 0, you go 3 to the left, and then you go 5 more to the left, and you find out that that equals -8. What I usually tell my middle school students or my college students is, I'm looking at this, and a -3 and a -5, they have the same sign. They're doing the same thing. They're going the same way. So I just would add 3 and 5, get 8, and then keep the sign, which makes it -8. Absolute value. Absolute value means just plain distance. How far away from 0 are you on the number line is about the best way to talk about it. If you are at your house and you walk 3 miles to the right, how far away from your house are you? You're 3 miles away. If you, on the other hand, walk 3 miles in the other direction and I say, how far away from your house are you? You don't say you're negative 3 miles, you just say you're still 3 miles. So absolute distance is thought of as, or absolute value really is distance from zero. Absolute value is always a positive value, or it's zero. So the absolute value of x equals x if x is greater than or equal to 0. Absolute value of x equals negative x if x is less than 0. I don't agree with that. Why does the book have that on a slide? Absolute value of x cannot equal negative x. It's always negative. It's always a positive x, no matter which way you go. Absolute value is positive. Many of my middle school students overgeneralize and think that the absolute value symbol means just to change the sign. So if they saw that absolute value of negative 8, they would make it a positive 8. If they saw absolute value of a positive 8, they may make it negative 8. This is not true. You don't change the sign. You just make the value, whatever value is in between the absolute value symbols, you make it positive. But this is just something, if you're working with students, to watch out for. So evaluate these absolute values. Absolute value of 20 is 20. Absolute value of negative 5, we just change it into a positive 5. Absolute value of 0 is 0. Now this one's tricky because the absolute value bars are grouping symbols, and some of you may have heard of PEMDAS. In my world, I call it GermDOS because P stands for parentheses. I look for any grouping symbols. That's why I have G. E is exponents. This is order of operations. We'll get to this in a little bit. I say, well, we have exponents, but we also have radicals because my students don't necessarily understand that x to the 1/2 is the same as square root of x. It's the radical. So we do, these are inverse operations. We have the inverse of multiplication is division. We have the inverse of addition is subtraction. I figure my students need to realize that the inverse of an exponent is a radical, and so that's why I have the R there. G is all grouping symbols. So absolute value is a grouping symbol, so I have to simplify what's inside there first. Absolute value of negative 3 equals 3, but then I have to apply that negative sign, so it's still there. This one, absolute value of 2 plus negative 5, I have to do the operation first because I have to solve what's inside the grouping symbols before I apply the absolute value. So on my number line, if I'm at 0, I'm going 1, 2 to the right because I have a positive 2. Then I'm going to turn around and go 5, so that's 2 to the right. I'm going to go 5 to the left, which brings me down to negative 1, negative 2, negative 3. So that is now the absolute value of negative 3, and then I apply the absolute value sign and I get a value of 3. Properties of integer addition. Integer addition has the properties of whole numbers. It has the closure property. So if you add two integers together, you are going to get an integer. So if I add negative 3 plus 4, that's the same as, I can change the direction. There's another way of thinking of it. As long as I keep the sign with it, I have a plus 4 and a minus 3. We know 4 minus 3 is 1. One integer and another integer gives me an integer. So the closure property holds true. Commutative property of addition says it doesn't matter what order you add things in, you have the same value. So a plus b is the same value as b plus a. Associative property of addition of integers doesn't matter how you group them. A plus b, do that math, and then add c gives you the same value as doing b plus c and then adding a. So that's the associative property. The identity element is what can you add to a value that doesn't change the value. So what can, if I have 8, what can I add to 8 that will still give me 8? And the answer is I can add 0. So 0 is the identity element. And additive inverse, that's related to the identity, but it's what if I had 8 again, What can I add to 8? That will give me 0. So additive inverse will cancel it out. What can I do? I can add a -8, and that will give me 0. By definition, the additive inverse, -a, or opposite of a, is the solution of the equation x plus a equals 0. So what can I add to a to make it 0, or what can I add to x to make it 0, whichever way. For any integer a and b, the equation x plus a equals b has a unique solution, b plus the opposite of a, or the inverse of a, or -a. So for any integers a and b, the opposite of -a equals a. So two negatives equals a, and -a plus -b, you can combine those two inside parentheses and just have the one negative sign outside. So find the additive inverse of each of the following. I can't, and again, we haven't gotten to distributive property, we'll get to that later, but I can't help saying that whenever I see this kind of situation, I'm going to say it's a -1, and I distribute that in. Just that's what we do in algebra. So -1 times 3 makes -3. -1 times a positive x makes a negative x. But then we're supposed to find the inverse of those. So what can I add to this to make it be 0? Well, to get -3, I have to add a positive 3, and I have to add a positive x. So that's why I'm going to add 3 plus x. A plus a -4, what can I add to that to make it equal to 0? So I'm looking for what can I do. A plus a -4 equals 0. What can I add to it? Well, to make a go away, I have to add a -a. To make a positive 4 go away, I have to add a positive 4. So I have -a plus 4. And what can I add to -3 plus a negative x? I have to put in parentheses there to show that the negative sign belongs to the x. And what can I do to make it 0? So I'm going to have to add a 3, and I'm going to have to add an x. So I have 3 plus x equals, added to this will make 0. So this is all additive inverse. Integer subtraction on the number line. While integer addition is modeled by maintaining the same direction, moving forward or backward depending on whether a positive or negative integer is added, subtraction is modeled by turning it around. So you're going in the opposite direction. So if I have 4 minus 3 on the number line, I'm going to start out at 0, and I'm going to go to the right, positive 4. 1, 2, 3, 4. So I'm going to be there, and then I'm going to go, oh, I changed direction, so instead of going right, I'm going to go to the left 3 units, which gives me 1, gets me back to the 1. That's the number line. Sometimes the pattern model for subtraction is an easy way to get people to visualize where these negative integers come from. So we just start out, and it's also related to show how exponents work, and fractional exponents, things like that. Same kind of pattern, that if I have 5 and I take away 1, I have 4. If I have 5 and I take away 2, I have 3. If I have 5 and I take away 3, I have 2. So as the numbers I'm taking away increase, what's happening to the difference? They're decreasing. So if I have 5 and I take away 4, I'm at 1. If I have 5 and I take away 5, I'm at 0. If I have 5 and I take away 6, what's going to happen? That has to decrease by 1 each time, because the value I'm subtracting is increasing by 1, so my answer, my difference, has to decrease by 1, and that's where the -1 comes. 5 minus 7 will be -2. 5 minus 8 will be -3. And sometimes this helps students understand where the negatives are coming from. Subtraction using the missing addend approach. Frankly, this method drives me batty a bit. I think it adds an extra step in there that can be confusing, but I know there are some of my colleagues at work do this all the time, and so I end up getting 8th grade from some of my 7th grade teachers, and the students deal with this, and they deal with it just fine, so I don't try to undo them, but um, if you have 3 minus 7, what they're saying is, okay, 3 minus 7 equals n only if 3 equals 7 plus n, and so because 7 plus 4 equals 3, n equals negative 4. So what they want to do is they kind of sometimes want to add the opposite, yeah, which gets me. This way I understand it because 3 minus 7 equals n. Well, we can add n 7 to both sides, so we get 3 does equal n plus 7 is where that can come from, and it does work out. I would say, well, then let's go ahead and subtract 3 from both sides, and we get 0 equals n plus 4, but then we want to get n by itself, so we have to subtract 4 from both sides, and we have negative 4 equals n, but that's just the algebra in me that's coming out right now to get that. For integers a and b, a minus b is the unique integer n such that a will be equal to b plus n. So they're saying a minus b equals n, but a, you add b to both sides, and you end up with a, because those undo each other, equals n plus b, but then they're taking this plus b and sticking it in front of the n, so a equals b plus n is what they're saying. Use the definition of subtraction to compute the following. So let 3 minus 10 equals n. Then you're going to add 10 to both sides. So 3 minus 10 equals n. If we add 10 to both sides, we get 3 equals n plus 10. And again, this is all extra steps, but you can subtract 3, so 0 equals n plus 7, and then we isolate the n by subtracting 7 from both sides, so we find out that n has a value of negative 7. Negative 2 minus 10 is equal to n. Again, they're going to say, well, let's add 10 to both sides. That's fine because now we have negative 2 is equal to n plus 10, and we can add 2 to both sides. So we have 0 is equal to n plus 12, and then to isolate the n to find the value of n, we subtract 12 from both sides and see that negative 12 equals n. I tend to just look at the problem. Now that I've shown you kind of the way the book wants it, and I say, well, 3 is we have a plus 3 and we have a minus 10. The signs are different. That means there's going to go one way on the number line and then back the other way. So since the signs are different, we can perform a subtraction, which makes 7. And then 10 is bigger, so it's going to travel 10 in the negative direction more than will travel 3 in the positive direction, so we have to keep the negative sign. And so that's how I would do that. I say negative 2 minus 10. Well, we have a negative 2 and a negative 10. On the number line, they're just going in the same direction. They're adding to each other. So I do an addition and get 12, and then it's going in the negative direction, both of them, so I have to add the negative sign. Oh, this is the thing I was complaining about earlier. Subtraction using adding the opposite approach. So a minus b is equal to a plus plus a negative b, or a plus the opposite of b. So if we have 2 minus 8, we have a positive 2 and a negative 8. They're going in opposite directions on the number line, so I'm going to do a subtraction, get 6. 8's bigger, so I keep the negative sign. I'd have 2 negatives in a row. So on a number line, what that means is the 2 is positive. So if I start out at 0, I'm going to go to the right, 2. But then I'm going to go, oh, I changed directions to go negative, but then I changed directions again. So I'm going back to positive, so then I'm going 8 more. Double negatives, and you're subtracting the opposite of 8, or doing the opposite of subtract 8, whichever way you want to think about it, they become a positive, so I actually have 2 plus 8 equals 10. Now I have a negative 12 minus a negative 5. I'm going to say, but those two negatives becomes a positive. So I have a negative 12 and a positive 5. They're undoing each other, going opposite directions in the number line. So I'm going to perform a subtraction. 12 minus 5 is 7. 12 is a bigger value. It's a heavier value. So it's going to go more negative than it is positive. So that means I have a negative answer. Negative 12 minus 5, they're adding to each other. They're going in the same direction. So I add 17, and they're going in the negative direction, so it's going to be a negative 17. This one, I have a negative out in front, so I have a negative 1 times b minus c. So I have a negative 1 plus b, or times b, which is going to give me a negative b, and a negative 1 times a negative c is going to give me a positive c. Again, I have a 1 there, so I have a negative 1 times b gives me a negative b, and negative 1 times a positive c gives me a negative c, and so there would that would be that. Some more. Again, I have a negative 1 there, so I'm going to have 2, and then negative 1 times 5 makes a negative 5. Negative 1 times a negative 6 makes a, x rather, makes a positive x. 2 minus 5, a positive 2 minus a 5. We're going in opposite direction, so I do 5 minus 2 is 3, and 5 it's going to go more in the negative direction, so it's a negative 3, and then plus x. Negative 1 I'm going to distribute in, so I have 5 minus x. Negative 1 times negative 3 is a positive 3. So I now can combine like terms. I have a positive 5 and a positive 3, which gives me a positive 8, and I still have that negative x. This negative is going to distribute in, so I end up with a negative x. A negative times a negative makes a positive y, and then I still am subtracting a y. I can combine like terms. A positive y and a negative y undo each other, so that's going to leave me with a negative x. Now we get into order of operations, where I called it GermDOS, because I want people to realize all grouping symbols have to be taken care of first, not just parentheses, but also curly braces, square brackets, absolute value signs, a division bar where you might have 3 plus 4 divided by 7 minus 8. This division bar is a grouping symbol also, where it says you have to simplify the numerator and simplify the denominator before you go on. So there's lots of grouping symbols. And then exponents and radicals, because they are the inverse operations, just like multiplication and division, addition and subtraction. And we take care of these groups in a left to right pattern. So solving a complicated equation, I'm going to go through and simplify anything in grouping symbols. Then I'm going to go left to right, repeat it until I'm done with all exponents and radicals. I'm going to go left to right continually until I'm done with all multiplication and division. And then I'm going to sweep back through taking care of all addition and subtraction. So an expression such as 3 minus 15 minus 8, it's kind of ambiguous. Some people might do 15 minus 8 is 7, and then 3 minus 7 is a negative 4, or you do 3 minus 15 is a negative 12, and take away 8 more is negative 20. There's a big difference. So what happens, I don't know, thousands of years ago, hundreds of years ago, is mathematicians got together and agreed that negative 3 minus 15 minus 8 means do the 3 minus 15 first and then the minus 8. So as I'm going through this, I'm looking for any subtraction. I'm going to take care of the subtraction as I find it. So 3 minus 15 will make negative 12 minus 8. I rewrite it, then I start back over and I take the subtraction, but I see that I now have two negative values, and so I can add them. I get 20, but they're going negative. So subtractions are performed in order from left to right. Exponents and radicals are also. Multiplication and division is also, and so is addition. So what do? I go left to right. Oh, look, there's a subtraction. So 2 minus 5 is negative 3, and I still have that negative 5, and then I can see that they're both negative, so I add them together, get 8, and keep the negative sign. Addition and subtraction are equal in importance, so I take care of them left to right. So there's a negative sign. 3 minus 7 is a negative 4 plus 3, and then I start over. I have a negative 4, add 3 makes a negative 1. I have to distribute the negative through first, so I have a 3, and then I have a negative 7, and then I have a positive 3, but I take care of this. 3 minus 7 is a negative 4 plus 3, which gives me a negative 1. The number line model. Demonstrate multiplication by using a hiker moving along a number line. Traveling left or west means moving in the negative direction. Traveling to the right or east means moving in the positive direction. Time in the future is denoted by a positive value. Time in the past is negative. I don't usually use a hiker. I usually just draw a little bug-shaped character and call him Freddy the Ant or something like that. If you're now at 0 and move east, that's to the right, at 3 miles per hour, where will you be 4 hours from now? So we're talking about groups of 3. So you're going 3 miles in each hour, and you have 4 of those hours, so you have 4 groups of 3. So there's one group of 3, 2 groups of 3. Wait a minute. 1, 2, 3. 3 groups of 3 and 4 groups of 3. You'll be at 12, or 3 times 4 is 12. If you're now at 0, moving east, so you're still going to the right, where were you 4 hours ago? So you're still moving groups of 3, but it was 4 hours ago. So there's 1 hour ago, 2 hours ago, 3 hours ago, 4 hours ago. You were at negative 12. If you're now at 0 and you're moving west, so now you're going to the left at 3 miles per hour. Where will you be 4 hours from now? 1 hour, 2 hour, 3 hours, 4 hours. You're moving 4 groups of 3 again. And if you're now at 0 and you're moving west at 3 miles, where were you 4 hours ago? That would be you're moving in a negative direction, but you were 4 hours ago is a negative number, so that makes you at 12 because you have negative 3 going in the negative direction, 3 miles an hour, and you have, but it was 4 hours ago, so it's negative 3 times negative 4. The closure property of multiplication of integers. When you multiply 2 integers, you will get an integer. That's what it means by a closure property. You have members of the integer set, and when you apply multiplication to them, they will still be an integer, whether it's negative and positive. So you have a negative 2 times 3. 2 times 3 is 6, and there's 1 negative, so it's negative. That is an integer. If you have 2 negatives, 2 positives, they are all integers. The commutative property, remember commutative is to commute, to change. So we change the order. A times B gives us the same value as B times A. Associative property, you can group things. Associative does mean grouping. So A times B, and then multiply that to product times C. It will give you the same values if you multiply B times C and then multiply that product by A. The identity property of multiplication. What can I multiply 3 by and not change its value? Some students in middle school say 0 because they know the identity property of addition we just talked about. But then I have to say, well, what does 3 times 0 equal? So what can you multiply 3 by is 1. So 1 is the identity property. A distributive property. I have, this shows A times the addition of B plus C. So it's a distributive property over addition. It also works over over subtraction. So this is where you have 3 times x minus 4 in an algebra problem, and you're multiplying. You're saying 3 times x is 3x, and a positive 3 times a negative 4 is a negative 12. So that's the distributive property. You're distributing this value over this subtraction problem. The zero multiplication property, any value multiplied by 0, you get 0. So negative 1 times A gives you a negative A. Negative A times B is the same thing as B times negative A. Commutative property, and that gives you, because a negative times positive is a negative, A times B. The negative A times negative B, 2 negatives will give you a positive, so you have A times B. And this is distributive property again, where you are going across. So that's a times b, and then a times negative c gives you a negative ac. Simplify each of the following so there are no parentheses. This is distribution, so we have negative 3 times x equals negative 3x, and we have a negative 3 times a negative 2, which negative times negative is a positive, 3 times 2 is 6. This one is distribution, so I'm going to distribute the a across first. So a times a is a squared. A times negative b is a negative a times b. Then I'm going to distribute the b across. A positive b times a positive a is a positive, and keep them alphabetical because remember the commutative property doesn't matter what order you multiply in. And then plus b times a negative b is going to be a negative b squared. And what do I notice? A negative ab and a positive ab are going to cancel each other out. So that's a squared minus b squared. This result is called the difference of squares. So whenever you have a value squared and you're subtracting another value squared, you can apply the difference of squares and you factor it back out to a plus b times a minus b. So use the difference of squares. I have a plus b, a minus b, so that's going to give me 4 squared minus b squared, and I can simplify that by saying 16 minus b squared. I have negative 4 times negative 4, so I have a plus b, a minus b, so that's going to give me a negative 4 squared, but it's going to be a negative b squared, and negative 4 squared is 16, so that's going to be 16 minus b squared. So I think they're trying to show you that it can work out to be the same way. So 16 minus b squared can either be a positive 4 plus b times 4 minus b, or it can be a negative 4 times plus b, negative 4 minus b. When the distributive property of multiplication over subtraction is written in reverse order, so we're used to seeing now a times b minus c. We're distributing across and gives us ab minus ac. We can if we see this version in it first, we can work it backwards by saying, well, we have a common factor we can pull out, and then what do we want? We have the b minus c inside, and this is factoring. This is an algebra skill generally. The difference of squares formula and the distributive property of multiplication over addition and subtraction can be useful tools in factoring. And if you ever run into factoring, I recommend you look up or you search for the diamond method. If you ever get having to factor things like ax squared plus bx plus c, anytime you have to factor quadratics, look up the diamond method. So factor all these. Well, we have a square, and that's actually a square, so if we convert that into 3 squared, we can factor it as using x plus 3, x minus 3. And so here we have a value squared minus a value squared, so the difference of squares comes into effect again, and we end up with x plus y plus c times x plus y minus z. So we have that that value plus z and that value minus z based on the difference of squares. There are no squares in this one, but I see that I have a common factor I can pull out. So that means I take out the x, and what am I left with? I'm left with a negative 3 plus 5y. What can I see I can take out? I have common value in there. I have a 3 because 6 can be broken down to 3 times 2. So if I take out that common 3, I have the 3, and what's left is the x and the minus 2. Here I have a difference of squares. And so 5x squared minus 2x squared. But what can I also do, though, is it doesn't work because the square really only applies to the x's. But I do have an x squared that's common among both of those. So if I pull the x squared out, I have 5 minus 2. And 5 minus 2 is 3. So then I have 3x squared. Integer division. If a and b are any integers, then a divided by b is a unique integer c if it exists, such that a equals b times c. So I'm taking A and cutting it up into B number of groups, and each group will have C items. So if each group has each B groups have C items, it will give me the total number of items back. The quotient of two negatives is a positive, and the quotient of a positive and a negative is a negative. That's just saying if you have negative A divided by negative B, you're going to have a positive A divided by B. And if you have a negative a divided by a positive b, you're going to have a negative a divided by b. So we have 12 divided by a negative 4. That's a positive divided by a negative, so I know my answer is going to be negative. And I also tell my middle school students and college students that negative signs can be sneaky, so be careful with them and take care of them first. So then now that I know that my answer is going to be negative, I can ignore it. 12 divided by 4 is 3. Negative 12 divided by 4, a negative divided by a positive, I know that's going to be a negative, and now I can ignore it. 12 divided by 4 is 3. A negative divided by a negative, I know is positive, so now I can ignore those negative signs, and 12 divided by 4 is 3. A negative divided by a positive, I know is a negative, and but it's not an even integer. It doesn't work out. I can leave it as a fraction, negative 12 fifths, or we just say it's undefined over the set of integers because there is no integer such that negative 12 divided by 5 equals an integer. So closure does not exist for division because, and that's an example of why not. Order of operations on integers. Again, here's where I say germ-DOS, and many people will say PEMDOS. So this is what most of the world talks about. People will look at you crazy if you talk about that. Although I've met a few teachers at the high school who say, "Oh, you're the one that's doing germ-DOS," because my students learn it and move on. But it says addition, subtraction, multiplication, division, and explanation appear without parentheses or without grouping symbols. Then we take care of exponentation first, the E. But then I also say, well, what about radicals? Because radicals are the inverse operation of exponentation. So that's where my R comes from. And then you do those in left to right through the problem. And then multiplication and division is what's next, M and D. But they're of equal importance, so you take care of them moving left to right through the problem. And then finally you go back and take care of addition and subtraction, again moving left to right. So I'm looking at any grouping symbols? No. Any exponents or radicals? No. Any multiplication or division? Yes, right there. I have a negative 5 times a positive 4. So that's going to leave me a 2. I move that along. What's negative 5 times positive 4 is a negative 20, and I'm not doing anything with the plus 1, so I put it there. Any more multiplication or division? No. So now I'm looking for addition and subtraction. Well, there's subtraction. 20 take away, or 2 take away 20. A positive take and a negative. Signs are different. I do subtraction. 20 minus 2 is 18. 20 is it's going to go more in the negative direction, so that's a negative 18. And then plus the 1, it just comes along. And then I start back over the beginning. Any more subtraction? No, but there's addition. Negative 18 plus 1. Signs are different, so I'm going to do subtraction. 18 minus 1 is 17, but it's going more negative than it is positive, so that's a negative 17. I have a grouping symbol, so I have to do 2 minus 5 first. The signs are different, so 5 minus 2 is 3, but it's going more negative, so that's a negative 3. And then this is hidden sign in there says times 4 plus 1. So now I have a negative 3 times 4, because there are no exponents or radicals. And so that's a negative 12 plus 1. I'm done with multiplication and division, and now I can take care of this addition. but they're going in opposite signs, so I do subtraction. 12 minus 1 is 11, and it's going more negative than it is positive, so that's a negative 11. C, I'm looking, I don't see any grouping symbols. I don't see any exponents or radicals, but I do see a multiplication problem right here. I have a negative 3 times 4, so that I'm going to bring the 2 along. Negative 3 times 4 is negative 12, and then plus 5 times 2 minus 1 plus 5. And I'm going to start over looking for multiplication, and I see I have a plus 5 times 2, so that means I have a 2 minus 12. Plus 5 times 2 is plus 10, excuse me, minus 1 plus 5. I have no more multiplication division, so I'm going through left to right looking for subtraction and addition. 2 minus 12, that makes 10 minus, or 12 minus 2 is 10, but it's more negative that direction. Then plus 10 minus 1 plus 5. And then I have a negative 10 plus 10. They undo each other. And so I have a negative 1 plus 5. Opposite signs, so 5 minus 1 is 4, and it's more positive than negative, so it's a positive 4. D, no grouping symbols, no exponents or radicals. Multiplication or division, I have a positive 16 divided by 4, so I bring that 2 along just because it's not involved. Positive 16 divided by 4 is positive 4, and then I have a times 2, and I have a plus 8. So now I'm going to go back through looking for multiplication and division. I have a plus 4 times 2, so the first 2 comes along just because, and a plus 4 times 2 is a plus 8, and then I have a plus 8. No more multiplication or division, so I'm looking for addition and subtraction. There's an addition. 2 plus 8 is, they're both positive, so we add them and we have 10, and then plus 8, and we have 10 plus 8, they're both positive, so we add them and we have 18. O, E, and F, these two problems are lovely. Many people will look at these and say the answers should be the same. In fact, yeah, but let's see, are they? Well, this says the base is negative 3, so what that really means is I'm raising negative 3 to the 4th power, or I'm multiplying negative 3 by itself 4 times. So negative 3 times negative 3 is a positive 9. A positive 9 times a negative 3 is a negative 27. A negative 27 times a negative 3 is a positive 81. Now here, the base is 3. The negative has nothing to do with it yet. I have to take care of exponents and radicals before I take care of the negative. So here, I have a negative sign, but then what I'm doing is I'm multiplying 3 by itself 4 times. 3 the base times itself 4 times. So 3 times 3 is 9, times 3 is 27, times 3 is 81. But then I deal with that negative sign, and it's negative 81. So negative 3 to the 4th power is not the same as negative 3 to the 4th power. These are different. And what gets confusing about these is if the exponent is odd, it appears to work. So negative 3 to the 3rd power, it appears to be the same. It does give you the same value as that. So when the exponent is odd, what we end up with is negative 3 times negative 3 times negative 3, or positive 9 times 3 is a negative 27. And this is a negative 3 times 3 times 3, or 9 times that, 27, and then we tag on that negative. So they do get the same value, but for different mathematical reasons, and this is one reason why it's easily confused, and kids get frustrated because it works when the exponents are negative, but when the exponents are positive, then you really see what's going on, and it does not work. Definition of less than for integers. For any integer a and b, a is less than b, written a is less than, and yes, that's not the alligator looking to the right or whatever the alligator wants to. It is, this is definitely a less than sign. This is definitely a greater than sign. Which end do you bump in as we are reading number sentences? Which end do you bump into first? You bump into the small end. That means that you bump into the less end. Which end do you bump into first? You bump into the more end. It's really tempting to fall into the alligator eating the cookie and all that, wanting to eat more cookies and stuff. Kids seem to get it, but it's mathematically incorrect, and it really doesn't help them by the time they start getting into 8th grade, because we start seeing numbers like 3x squared is bigger than um, 8x plus 4, and we've got to deal with it. They look at this and they have no idea which side is bigger and things because of the variables. So I just say you've got to learn as you're reading the number sentence, and we read from left to right, which end do you bump into? Do you bump into the less end or the more end? So this is A is less than B. If and only if there exists a positive integer k such that a plus k equals b. So properties of inequalities of integers. X is less than y and n is any integer, then x plus n will still be less than y plus n. That's the addition property of equality, saying that you can add the same value to both sides of your inequality, and you don't change the fact of the inequality. If x is less than y, then the opposite of x is bigger than the opposite of y. This is important when simplifying inequalities, to realize that if you're going to multiply or divide both sides of an equation by a negative, then you have to change the direction of the inequality sign. On a number line, if we have 0, and let's see, x is less than y. So here's x, here's y. X is less than y. But if I multiply it by a negative, I end up with a negative x, and I end up with a negative y if I multiply both of them by a negative 1. And now x is to the right of y, and so we know that that sign still is there, so now negative x is bigger than negative y, because negative x is further to the right than negative y, whereas positive y is further to the right, to the bigger end of than x. If x is less than y and n is greater than 0, then you multiply both sides, and the inequality sign doesn't change at all because n is bigger than 0. But if x is less than y but n is less than 0, well, then we're into this situation that I just demonstrated on the number line, because now n is a negative number, so we're multiplying both sides of the inequality by a negative number, so we have to change the direction of the sign. Find all integers x that satisfy the following. What values are worth x? And to find that, I have to isolate x. To isolate x, I have to subtract 3. The subtraction property of inequality says if I subtract 3 from one side of the inequality sign, I have to subtract 3 from the other side of the inequality sign. So that leaves x, because plus 3 and minus 3 undo each other. I'm not multiplying or dividing both sides by a negative, so the inequality sign stays in the same direction. And negative 2, and I'm taking away 3 more there, this going in the same direction, so I add and get 5, and it's negative. So any value of x that's less than negative 5, and the best way to show this is on a number line, if they let you. Well, there's 0. There's my value of interest is negative 5. It's just a less than sign. It's not equal to, so I put an open 0 at 5, and x is less than that. Less than is to the left side, so I shade in there. So any value that's less than negative 5 is what x is. Now I can do the same thing here, and I add 3 to both sides. So I have negative x is less than, they're both positive, 8. Do I want to know what negative x is? No, I don't want to know what negative x is. So I have to divide, or either multiply both sides by a negative 1 or divide both sides by a negative 1. The same thing is accomplished. A negative divided by a negative leaves me a positive. A positive divided by a negative leaves me a negative. But since I divided both sides by a -1, I have to change the direction of the sign. So I now have x is greater than -8. And so on a number line, there's 0. There's my number. My value of interest is -8 because that's what x is bigger than. There's no equal sign, so it's open. And x is bigger than that, and the bigger than side is to the right, so I'm going to shade the number line to the right to show that any value bigger than -8 is satisfies for x. I keep saying if there's a line, if it was x is greater than or equal to -8, then on the number line, what I would have done is put a filled in circle to indicate that -8 also satisfies the equation or the inequality. When I was going through the homework in my math lab, I noticed that they use function notation one time. Function notation, the easiest way to understand it is just that f of x is replacing the y in the equation. So if you have y equals 4x minus 7, to write it in function notation, you just write f of x is equal to 4x minus 7. And really that just means that it's the function f solve for the value of x. That's what f of x means. Because you can also have the function g solve for the value of x is 3x plus 19. And you can have the function h solve for the given value of x is equal to -7x minus 11. Things like that. So the f really in this is just the function name and it's saying solve for the value of x. So if you're given a problem like f of x equals -3x plus 4, find the value of the function for the value of x equals -3. That's what this says. What this means is I take that -3 and I plug it in for every x. So I say f, the function f, solve for the value of -3 is equal to -3 times -3, because I substituted that x in, or that -3 in, plus 4. So the function evaluated for the value x is -3 is equal to, well, -3 times -3 is a positive 9 plus 4. The function evaluated for the value x is -3 is 13. And so f of x is read f of x. That's what I'm saying. F of x. Really, just the easiest way to think of it is it's just replacing y, but as we move on into upper level mathematics, we may have more than just one equation. And so if you keep saying y is equal to this, y is equal to that, if we keep having y is equal to 3x plus 19, and then say y is equal to -7x minus 11, and then say y is equal to 4x plus 2. It gets a little confusing about which equation you're talking about. That's why we start naming the equations, and they're actually functions. And the definition of a function is that for every value of x, there is a unique one and only value of y. And we can get further into that, but for the homework in my math lab, you just need to know that f of x just really is y.